Hello everyone, welcome to my YouTube channel. In this tutorial, I will be explaining how to perform principal component analysis and how to generate free energy landscape using GROMACS trajectory. So in this tutorial, I am going to use a protein molecule bound with one known inhibitor and one test compound. Okay, then we'll see when this chemical compound, that means inhibitor and the test compounds, are bound with the protein molecule, how does it behave during MD simulation? Do they behave differently? Whether their structural alteration during MD simulation are different? So to analyze this, we will use principal component analysis. Okay. So in this tutorial folder, two different folders are there, control and test. And within this control folder and test folder, you can see these are the input files, the trajectory file, XTC file, TPR file, index file, and .gr file. So these two file mainly important, TPR and XTC file. And then open this folder in terminal, and this is for control. And now these are the commands which we are going to use. So first of all, it's better to remove the rotational and translational motion from the trajectory. That means you need to refine the simulation trajectory using the trajectory conversion command. And this is the command for trajectory conversion. So from simply mdcenter.xtc, we are going to transform it into fitted.xtc. Okay, this is the command. Simply copy it and paste it into the terminal. Now it will ask to select a group for least square feet, and we are going to use the backbone, protein backbone for least square feet, and as output we will select the whole system. Okay, so now select for output whole system, that means group 0, and the whole trajectory will be defined. That means rotational and translational motions will be removed from the trajectory, and we'll get a fitted dot XTC, this trajectory. And we'll do this same for the test group also. This is for test. Paste the same command and refine the trajectory. So the simulation time is 150 nanosecond, and we have refined our trajectory. Okay. Now we'll use this fitted.xtc for our principal component analysis. And the next command is GMX covar, that means covariance. Okay, so cover module of GROMACS will be used, and as input file fitted.xtc and TPR file, and as output we will get eigenvector.trr. Okay, and we will select the group 3, that means C alpha, for principal component analysis. You can also use backbone for principal component analysis, but more number of atoms, more time will be required for performing the covariance matrix calculation. So we are selecting the group 3 for least square feet, and also for calculation of covariance matrix we are selecting group 3, and for both the control and test group. So covariance matrix calculation is complete, and we have obtained eigenvector.trr file. This is the most important file. All the covariance are written in this eigenvector.trr. The direction of movement and degree of movement, everything is recorded. Now the next module, that means NIH, it will be used, and as input we are going to use eigenvector.trr, and we will obtain a 2D projection. So the command 2D is for obtaining the 2D projection.xvg. And you know, for 2D, two axis will be required. First axis is first principal component, second axis is second principal component. That's why first one and last two. Okay, so we will get a 2D projection. Simply copy and paste this command to obtain the 2D projection. And also you'll be prompted for group selection, group 3 for least square feet, and also obtaining for 2D projection. Now we have obtained 2D projection.xvg, and we can visualize it using XMGrace or QtGrace software. Okay, these are the plotting software, you know. So we can compare the projection, 2D projection of a protein molecule which is bound to different compound. Okay, to check whether their projections are different or not. That means their conformational space are different or not, and how much it is different. So this was for control, and now for the test group. So this is for the test group, this projection. Now you can convert this 2D projection to gives.xpm. That means we are trying to convert the 2D projection into free energy landscape. Okay. So actually the projection means the conformational journey of the protein molecule during the simulation time. So during simulation, protein attain different conformation, and within this 2G projection we get the different number of conformation. And when we express this conformation in terms of their energy state, so the projection is converted into the free energy landscape. So first of all, we have to convert the XVG file to XPM. Then you can convert from XPM to EPS. The EPS can be visualized. Okay, so let's convert it into EPS, and you can see the projection has been converted into free energy landscape. That means projection in terms of their free energy state. And this blue region is the energy minimum region. But you can see the EPS, the resolution of the EPS image is not so good. Okay, so for publication, we have a better option. We can convert the XVM file to the text file, and then using this data, we can plot it into a software like Origin to get better image. Okay, but if you don't have access to Origin, you can simply convert it into EPS and you can publish. But if you have access to Origin, uh, it's better to plot it in Origin. Okay, but for that you are going to need a Python script which will convert XPM to text. So you can download this XPM to text.py, this Python script, from the YouTube link I have already uploaded, and it is compatible with all Python versions. And this is the XPM to text.py, and you have to keep this Python script in folder, that means in working folder. Then simply copy this command python 3 xpm to text.py. As input we are going to use gives.xpm, and as output we will get gives.text. So now we have obtained gives.text, and this text file, the data from this text file, we can use to plot the free energy landscape in Origin software. Now, if you want to visualize the conformational change during simulation and along any principal axis, suppose you want to see the conformational change along first principal component. So use first one, last one, and use this NIA command and extract the extreme.pdb structure. Total 50 frames you can extract. You can extract more, but it's better to select 50 frames to get 50 frame dot pdb. That means extreme structure or conformation along the first principal component. So use this command, and once you have obtained this extreme.pdb structure, it you can use it for generation of the porcupine plot or sausage plot. So I will upload a tutorial on how to generate this plot, sausage plot and porcupine plot. For that, this extreme.pdb structure is required. Okay. So now we have obtained the extreme.pdb structure. This is the extreme.pdb. You can simply open it in VMD, okay, to see the conformational change along any principal component. So I have extracted it along principal component 1. Okay. But since we have performed principal component analysis on C alpha atoms only, so the structure looks like this. Only the C alpha carbons are present. So, uh, but if you want to visualize all the backbone, not only the C alpha, then you have to perform principal component analysis using the backbone. Okay. So more time will be required, but you will get this kind of structure, this kind of extreme.pdb, and it's better if you want to generate porcupine plot or sausage plot along any principal component. It's better to use the backbone. That means instead of group 3, you have to select group 4 for backbone. And simply watching this video, you can assess the conformational change along any principal component. Now it's time to visualize the 2D projection using QtGrace software. For that, open the QtGrace software. This is the QtGrace interface. And now I am going to show you a comparative 2D projection using QtGrace. For that, I am going to use conformational space of a protein bound with a known inhibitor. And this is the 2D projection. Similarly, for the conformational space of that protein but bound with a test compound. Okay. So now these both 2D projection are present in a single plot, and you can see when the test compound is bound with the protein molecule, its conformational space is somewhat different. It's restricted than the known inhibitor. That means binding of this test compound has restricted the structural alteration of the protein to some extent. Okay, so its conformational space is different. And now what is conformational space? That means the number of conformation the protein can attain during simulation. If the conformational space is very large, that means more number of conformation protein can attain during the simulation. Okay, and suppose I change it to the from the style of this left plot data for this dotted style. Okay, if I shift to this dotted style, then you can see this each dot is actually one conformation. Okay, so you can see more number of conformation. That means these conformation again are in 2D space. So in this particular point, along x-axis the first principal component, and along y-axis the second principal component. Okay, now among this conformation, suppose this part, okay, suppose this part, numerous conformations are there, and each conformation has its own energy state. So if we convert this plot into free energy landscape, we can see the region or the conformation with different energy states. So suppose in this region, all this conformation has low energy state. That means gives free energy is low in this region. That means these conformations are energetically favorable. Okay, and for that we are going to use the gis.text. Okay, suppose this is for control gis.text. So first, this is a text document, so I am opening it in Excel first. Okay, so open Microsoft Office Excel, and then go to data, from text, and select that text file. So you can see there are three columns. First and second column is the first and second principal component, and this third column is the energy state of that particular conformation. So simply copy it and then open Origin software. You can see here only two columns are present. So you need to add one extra column. Okay, now paste the data. Change this column name because this x column y and this should be z. So set as z. Okay, type here PC1, this is PC2, and this is G. Now select the data and click here plot, and I am using here the 2D plot, contour plot. Okay, and you can see this is the free energy landscape of the control group, and two global energy minima regions are present. That means the conformations which are present in these regions are more energetically favorable. So when the protein is attaining this conformation during simulation, so these conformations are more stable. So if any within any 2D projection or in conformational space, if more number of global energy minimum regions are present, that means the protein has comfortable zones. Okay, so in this zone the protein have energy minimized state. So the binding of the ligand may form stable complexes because the low energy states are present. But if within the conformational space there is no such blue region, that means low energy state region, so protein will try to change its conformation to uh, find a favorable region, a zone of comfort. So that means your protein complex is unstable until it finds any comfort zone or blue region. Okay, this is one of my published paper, and you can see this is the conformational space of protein bound with known inhibitor, and this is the conformational space of that protein when bound to a test compound. And these are the for test compounds, other test compound. And this compound, you can see when bound to the protein, it has more global energy minima region. That means binding with this ligand with the protein molecule can lead to a stable complex. So that's how you can interpret. Okay, and its conformational space is also restricted. Okay, same 2D projection, but it is in terms of their energy state. So that's all about free energy landscape, and now you know how to generate this free energy landscape and how to plot it in Origin software. So that's all for this tutorial. In next tutorial, I'll be explaining how to generate the porcupine plot and the sausage plot using that extreme.pdb which we have extracted along any principal component. Okay, so thank you for watching.